Yeah, so I think Dan will start and Alexander will continue on. So I think many people probably have heard of Dan, who is an expert on filtering, on SPD, and stochastic analysis in general. Honestly, I have not found so much about Alexander, but I'm sure he will introduce himself to this audience. And with that, Dan, please go ahead. And yeah, I'm looking forward to your talk.
Well, let me start by thanking, first of all, Rahul and AJ for the invitation to give a talk at this meeting, which looks great, by the way, and we are really very sorry that we couldn't be there. You know, we promise we're going to visit Coast on the first available occasion. And also let me thank Crisan for the introduction. Alexander is currently a PDRA in my group here at the Imperial. He has been finishing his PhD at the University of Oslo, and he's been supervised by Salvador Ortiz-Lator. And indeed, this presentation and this work is part of his PhD, and he's meant to have his viva later in the summer. So this is a talk on deep learning algorithms for nonlinear stochastic filtering problem, and it incorporates a case study for the Benesch filter. So what we plan to do is to sort of introduce briefly the stochastic filtering problem, and then explain the splitting method as applied to the filtering problem. And as you will see, there will be two parts. The splitting method has two parts. One where you produce, you update the prior, and then the other one where you do a normalization to get the posterior. The deep learning part is going to be applied to the prior, and then the update is going to be done by means of a Monte Carlo normalization. We will present the algorithm and then move on to show you some results where we tested the algorithm on the Benesch filter. This was our benchmark model. Benesch filter is an example of a nonlinear filter which has explicit solution, and therefore is a very good benchmark for any new algorithms. So there will be a presentation of the experimental setup and the results that we obtained, and we will conclude with some final remarks. As I said, we have a paper out, which is already on the archive, and I think it's already been published somewhere. Alex perhaps might remind me where it's published. There's a second paper which the second part of the talk is covered in the second paper, and again this is about to appear in proceedings of a recent annual meeting that we had last year. Okay, so let me start. So what is the stochastic filtering problem? Essentially, we have two ingredients. The first is the signal process, and the signal process satisfies this stochastic differential equation, and I'm going to assume that. Let me add my drawing in here. So we are going to assume. Oh, it doesn't work. Okay, I'll not. Let me just try again. So it doesn't work. Okay, never mind. So we're going to assume that we work in RD with the signal, and we have some observation process in RM, and F and sigma and H are properly chosen coefficients which satisfy the right conditions so that this system is well defined. The signal equation is driven by some Brownian motion which is p-dimensional, and the observation equation is driven by another Brownian motion W, which is m-dimensional. And for the purpose of this work, we're going to assume that V and W are independent of each other. And the filtering problem consists in computing or approximating or estimating the conditional distribution of the signal given the data, given the observation. This is denoted by pi t, and this is pi t of phi for any test function phi is equal to, by definition, the conditional expectation of phi of xt given the observation sigma field, which is, let me just move this away, which is given explicitly presented in here, is the sigma algebra generated by the observations, and it's augmented for technical reasons by all the null sets in the original space. Okay, so the point and the argument that the methodology that we will develop is going to be based on this Kalian-Pusch-Tibels formula. There is a representation of pi t, this conditional distribution of the signal, as a ratio of these two quantities. So to explain what this is, I need to go through this page. So what you do, you introduce a process zt, which is an exponential martingale. You use this process to generate a new probability measure p tilde, which is absolutely continuous with respect to p, and it has as randomly coding derivative this process z. And then you define this measurable variable process rho t, right? In this, by using this long expression, rho t of phi has this expression here, which is the conditional expectation with respect to the new measure of this quantity here, phi of xt times this exponential in here. And then once you have this measure variable process introduced, then there is a formula called the Kalian-Pusch-Tibels formula, which says that if you take this measure variable process and divide it by the total mass, in other words, the integral of 1 with respect to rho t, then you obtain pi t. So rather than computing pi t, you can compute rho t divided by the total mass, and then you end up with pi t itself. Well, what's the point of this? Well, the point of this is that whilst pi t satisfies this long and complicated equation, nonlinear SPDE, right? This is called the Kuznets-Platonovich equation. Rho t itself satisfies a much simpler equation. In fact, rho t satisfies a linear SPD, which is written in here, where this A here has this expression and is the infinitesimal generator of the signal. And H is the César function that appears in the observation equation. Okay, so in many cases, it's easier to look and study rho t and then normalize it to get a hang, get an expression to estimate pi t itself. Now there's more. You can show that rho t, this measurable process rho t, has a density with respect to the Lebesgue measure. And if you denote this density by pt, right, then you can write down the equation satisfied by the density, which is just the strong form of this equation. And the equation satisfied by the density has this expression in here. So I have an initial condition. Here, this A star, this is the formula joint of A. And then there's a stochastic integral in here, where this H perp here is the transpose of H. So essentially, this is just a sum of stochastic integrals, and we deal here with a multiplicative noise. So the aim is to try to estimate the solution of either of these equations. If you have one, you can have the others. And this is done by means of some numerical methodology. Now, there's been a lot of work in the last 50 years and even more on numerically approximating pi t. Pi t has, in very few situations, an explicit solution. For example, the Banach filter, which we will mention later on. But in general, pi t cannot be written explicitly. And what you need to do, you need to approximate it via some numerical methodology. And I put here three classes of methodologies that are out there. And they are perhaps the most successful methodologies that can be used to solve the filtering problem. Particle filters is one of them, and it's been developed a lot in the last 30 years, and nowadays it's sort of a very vast area where there are a lot of results. And I've just returned from a meeting in Madrid on sequential Monte Carlo methods, which is just another name for particle filters. There are also other methodologies, for example, ensemble Kalman filter and extending Kalman filter, that can be used to approximate pi-t, also very successful. And these methods are methods that are recursive, and that means that you can compute pi-t plus delta out of pi-t and the new observations, and that as a result of them being recursive, they can be used for online filtering. Now, if you want to read more about particle filters and so on, there's a lot of work done out there, and it's a Google search will tell you a lot about particle filters in general. Our work now is geared towards extending particle filters to high-dimensional filtering problem, such as the one that appear in numerical weather prediction. And we currently have a project that is dedicated to this. And I would like to try and show you this project. Maybe I can share this project at the end. Now, what I'm going to show you next, so this deep learning splitting method that we work on at the moment, is really at the beginning. This is still in its infancy. We hope to develop it, and we hope to combine it with some of the other existing methods. But at the moment, this method is still sort of far from being able to compete with sort of the elaborate particle filters or all the other methodologies that are out there. So we are, in some sense, at the beginning of the development of this type of deep learning techniques for filtering. Okay, so what I would like to do, I'd like to tell you a little bit about how what is the splitting methods for the filtering problem. And it's called the splitting methods because the actual update is done in 2 steps. It's split into 2 steps. So I've put here again the SPD satisfied by the density. So we have an initial condition, right? And then you have a term, a deterministic term, where you have here the adjoint of the infinitesimal generator of the signal. So this comes about as a result of the evolution of the law of the signal. And then you have the stochastic term that comes about as a result of having new observations coming continuously into the system. Now, the splitting methods, what it does, it recursively updates one and the other terms, right? So it starts with updating the first term, and then it moves and it updates the second term. So that's why the splitting comes from. So let me just explain what it is. So we have 2 steps, and they are called the prediction step and the normalization step. And so the first step, what it does, essentially, you forget about this term here, and you just assume that you have these 2 terms and really solve a PDE, which is given by this expression, an initial value problem that starts with the solution at time n-1, and sort of not n-1, some tn-1, and then you update it using by solving this initial value problem. The next step is the normalization step, where you say, okay, I arrived there, but I have to add back this term in there. And the way in which you add it back is by multiplying by this exponential, which inside the exponential you have the observation discretized over the interval tn-1 tn, and then you normalize it so that you keep it a probability measure. So in some sense, we don't really get the solution of this equation, but we get the solution of this equation normalized. So That means that we approximate not rho t, the unnormalized condition distribution of the signal, but we aim to approximate pi t directly. Okay, so that's the splitting method for the filtering problem. So what we want to do next, we want to say, okay, now we have this methodology. How are we going to solve this PD in here? So we're going to use deep learning in order to solve the prediction step in there. And the way this is done is, if you were to apply a standard, PD techniques with, a finite element or a finite grid and so on, then you'll need to specify a space discretization. You need to specify a grid, but because you use deep learning, you don't need to specify this grid. It's done via a neural network, and the result of that is that this is really very much conducing to the possibility of trying to apply this to a high dimensional state space. And this is what I'm saying in here. In order to solve the prediction step, we apply a feed-forward neural network that approximate the initial value problem based on some sort of stochastic representation by using a sampling procedures, and I'm going to explain that on the next page. The next step, the normalization step, can be done in two ways. You can either do it directly by using quadrature, or if you don't want to do that, if you don't want to integrate by using a mesh, you can use Monte Carlo approximation for the second step. Okay, so the note in here, which is, and I've already mentioned this thing, we don't have a priori a choice of the domain. The domain is not a priori chosen. Because it's mesh free, then the method is going to be able to be extended to general spaces. At the moment, you will only see a one-dimensional applications to the Beneš filter, and this is what we're currently doing. Good. So I need to tell you how we apply the deep learning methodology to the prediction step, and for this, I am writing this adjoint operator A star as a sum of two terms. The first term I denoted by A hat, right? And this is a second order differential operator. And is chosen so that it's the infinitesimal generator of a certain diffusion process X hat, or rather put it inversely, X hat is the infinitesimal, it has as the infinitesimal generator this operator A hat. And then in A star, you have a zero order term, which is just a function as this expression multiplied by the test function phi. Okay, so we rewrite A star as a sum of two terms. One is the infinitesimal generator of some diffusion process, and the other one is just a zero order term multiplication by R. And we have this, the well-known Feynman-Cast formula, which says that should you have an initial value problem of this form, right, with a multiplicative zero order term, and here with differential operator A hat, which is the A hat that we just seen, then you can write the solution of the of this Cauchy problem as an expected value of this expression, psi is the initial condition times this exponential condition here with respect to the x not being equal to x. So we have a Feynman-Cast formula for the solution, and it's this Feynman-Cast formula that we're going to exploit in our to train our neural networks. Okay, so going back now to our problem, I'm rewriting here the prediction step in exactly the form that is required to apply the Feynman-Cast formula, and then we have the solution of the prediction step in terms of the Feynman-Cast formula for the process X hat and this zero order term, which is the function R. Okay, so we use this representation. Okay, and in order to solve it, we rewrite the solution as an optimization problem, as the solution of an optimization problem. Okay, so what we do, we get some sort of basis support for the density, and then we assume in here that x0 is equal to psi, where psi here, for example, can be sort of uniformly distributed on the interval AB to the power D, and then we compute our Feynman-Caz representation by using this function u, which turns out to be the solution, and this is done by an optimization problem, as I said, over all functions v, which are continuous on this high-dimensional space with values in R. Good. Okay, now this is going to be done by using a neural network. Okay, and so in order to solve this Fokker-Planck equation over this rectangular domain, we will use a neural network. What we've done, we had a neural network that had L layers, and for each layers, in each layer, the width of the layer was Li. So we want to optimize. We want to compute the infimum of this expression, where the neural network appears in here, and the parameters vary over this space. Okay, so I'm going to stop here. I'm going to let Alex take over to explain how the neural network is built.
Okay, thank you very much, Dan. Let me just share my screen. Okay, can you see the slides?
Yes.
Okay, thank you. Right, so just take over here. Okay, so now just to recap the last few sentences that Dan introduced. So we are here having the theoretical optimization problem, which ensures that sort of we are targeting the right function using our neural network. So this establishes the existence of the right minimizer in the infinite dimensional space. And now we have this discretized function space, which is parameterized now by our parameter theta. And the parameter theta is the parameter of the neural network, which we will now optimize in order to obtain a neural network which, as closely as possible, approximates the theoretical minimizer capital U introduced in the proposition. And yeah, so this is done over, in general, any sort of rectangular domain in a d-dimensional space, and our subsequent examples will be for one-dimensional spaces. So what we do in practice is, so we use the Adam optimizer, and the machine learning people in the room will recognize the Adam optimizer as sort of the state-of-the-art, I guess, most used optimization methods for deep learning at the moment. So this is an extension of the classical gradient descent and stochastic gradient descent methodologies. And so our loss function, curly L, is derived from the minimization problem that we showed you on the previous slide. So the loss at a given parameter value theta, given a batch of training data, which consists of NB, where NB is the batch size, realizations of the initial value xi. So remember, xi is uniformly distributed over the domain, which means that we obtain a neural network which lives on this domain. and the realizations of the diffusion process X hat, which is the diffusion that we need in the Feynman-Katz formula. And so given a batch of these training data, we minimize this approximate mean of the difference between what we should get in the Feynman-Katz representation, which is the first part in front of the minus sign. So psi of X hat times the exponential of the discretized integral of R, or in this case, minus K, applied to the diffusion, and then the loss with respect to the neural network. So this is the difference between what the neural network represents on the domain and what the Feynman-Katz formula would give us. So yeah, as I said, NB is the batch size. So this is standard technique in machine learning to use batched gradient descent. And the training samples are independent and identically distributed, where if I have realized one of these psi i's as a random value inside the domain, then the diffusion X hat psi I is the diffusion started at that realization of psi I, so that I get a bunch of diffusions started at uniformly random values over the domain. And to simulate the diffusions, we simply used the Euler-Maruyama method over the time interval. And so since we have some additional structure in our problem, we decided to augment the loss further by adding a regularizing term. So we define our loss L tilde to be the loss curly L that I just showed you, which corresponds to the Feynman-Katz, to the direct Feynman-Katz loss, so to say, plus hyperparameter lambda times the sum over the batch of the maximum of 0 and minus the neural network. So what this does is it penalizes negative values of the neural network. And this is done because we know that the density has to be positive. And this is one way to sort of computationally ensure that the density, in fact, meets this constraint of being positive. Yeah, and we've put a little note here that says that sort of this regularizing term does not mathematically guarantee that the solution is indeed going to be positive, but it's often done in machine learning problems to sort of regularize the loss with these sort of constraints. And we found that computationally, this approach has worked well for us. But of course, there exist different methods and also sort of mathematically more rigorous methods to ensure the positivity of the solution. For example, you could exponentiate the neural network and then minimize the exponential of the parameterized neural network, and so that this thing is always positive. But yeah, this is more of a choice than sort of a strict requirement. You could imagine using different methods, but for us, the regularizing term has worked quite well. And one more important comment to make is that this method relies on postulating this neural network model for the density. And also, since we do not require an a priori sort of discretization of the domain, we need to make some assumptions on the domain, because we cannot sort of solve over the whole of RD, and that's not possible. So here we've made the assumption that the support of the density, or in fact the neural network, is our rectangular domain ABD. And therefore, it's crucial that the domain that we choose in the first instance does capture most of the probability mass of the real distribution. Otherwise, you start off with a very wrong domain and you will never obtain anything. So it's really important that the initial domain matches the domain of the actual initial density, which is not hard to do. But then sort of advancing the domain later is actually a much harder problem to ensure that you sort of stay on the right domain and move with the solution. And I will show later how this looks in our practical results. So this was about the neural network approximation of the prior, but Dan has also introduced the second step of the classical splitting method, which is the normalization, which is there to incorporate the observation process into our solution of the filtering problem. And so to perform this normalization step, we have used the Monte Carlo method. And in our one-dimensional setup, of course, this is more of an optional choice. You could just as well use a quadrature, but since we wanted to remain mesh-free, we thought to do it this way. So what do we have to do to compute this normalization? So what we need to do is, in theory, we need to take the integral over the whole space of the neural network against the likelihood function psi. And as I said, the domain of the neural network, the support of the neural network, is assumed to be our rectangular domain omega d. So in fact, this integral to compute the normalizing constant using this assumption is identical to the integral over our rectangular domain with respect to, so here we have written out the likelihood term, it's this exponential, and then the neural network integrated over the domain. And this Zn is this update term given the observations. So you have the observation ytn at time tn and the observation ytn minus 1 at time tn minus 1. And sort of in general, this is not that easy to do with Monte Carlo, and we thought for our examples in the Banish filtering case, we can take advantage of the sensor function little h, which is the function that relates the signal process to the observation process, is given by this one-dimensional affine form, h of x being h1x plus h2. So we can nicely exploit this fact because substituting this little h into the exponential in the integral leads us to see that the likelihood xi is given by this constant times the probability density function of a normal with a given mean that is found by, and that is parameterized by h1 and h2, and a given variance. So this is, of course, very nice because it is very easy to simulate now from this likelihood function because it's just a simulation of a normal random variable with a given mean and a given variance. So we can write this integral as the expectation over the law of z, so as the expectation of the neural network with respect to the law of z, where z is, as I said, the normal random variable with these two mean and variance terms. And now, using this fact, our method now is completely implementable, and we can also compute this normalization constant, which in general is the thing that requires sort of much thought. And so in the end, the posterior density that we find using our method is given by Pn of z, which is 1 over the normalization constant times the likelihood function times the p tilde n, and p tilde n is the neural network representation. So that means that since all of these terms are explicit, this method is also fully recursive, and we can apply it sequentially step by step in principle for an infinite number of time steps, provided that sort of we stay inside of our computational domain, or we have a way to move this omega d throughout time. Yeah, and I already mentioned this remark that in low dimensions, the Monte Carlo method is optional. Right, so in the interest of time, I will not be will not go into too much detail in the algorithm. So here we just summarize the algorithm. So we have a time grid, the initial density, we have the observations up to time capital N, and we need to require that the affine linear sensor function is linear or affine linear. And so we can go from the initial posterior P0 by just initializing a neural network, training the neural network given the previous posterior, computing all the terms necessary for the likelihood, sampling from this normal random variable, computing the normalization, and then defining this posterior at time n to be the new solution. Yeah, the network training is the classical Adam method. Here it's summarized for a gradient descent step, which I will not go into now. So our results are done for the Banish filter. So the Banish filter is a very nice benchmark model, as Dan already mentioned, because of a few nice features. So the first feature is it is a nonlinear model, which you can see. So if you look at the signal equation for xt, there's the integral over alpha sigma times the hyperbolic tangent. So this is a nonlinear model, and these nonlinear models can get very complicated. But in fact, for the Banish filter, the nice thing is that we have an explicit theoretical solution given, right? And so this is written here on this slide in Formula 6. So the solution of this Banish model is this density PB, which is a mixture of two Gaussians. So there's a weight W plus into weight W minus, and then there is capital phi, which is the Gaussian function with a mean mu and a variance nu, which are explicitly given by these formulas below on the slide. So that means that we can test our method against this exact solution of the Banish filter in the nonlinear case. And we have the parameter values alpha, beta, sigma, and H1 and H2 to play with additionally. And in our results, we found that tuning these alpha, beta, and sigma, and so on, is actually not a simple problem because you need to play with the signal to noise ratio and so on to actually exploit the maximum amount of nonlinearity, because it can happen that the solution moves too fast or too slow, and then sort of things are difficult to compute. And yeah, what we've done here, I'm showing here a simulation of the true solution of the Banish filter. And this is done because, as I said, the domain has to move with the solution in order to stay true to the domain of the neural network. So we need to sort of always capture the support of the posterior density. And so the green curve in here is the true posterior. All these sort of light gray lines, they are posteriors for varying observations, just so to show you what solutions potentially could look like for the Banish filter. The red line is the signal, and the bounding gray lines, the vertical bounding gray lines, they are our pre-estimated supports for the method. Yeah, and I've listed here the parameters that we used for the simulations. Right, the neural network architecture, as Dan already mentioned, was a feed-forward neural network. The input layer is one-dimensional since we are working on a one-dimensional domain. We use 2 hidden layers with 51 neurons each, and the output layer is again one-dimensional. And additionally, we use the batch normalization layers in between. The spatial resolution is 1000 uniformly spaced values in the domain of the neural network. We train using the Adam optimizer with 6,002 epochs at each time step and a batch size of 600. And the learning rate follows a piecewise constant schedule. And the normalization was performed using 10 to the minus 7 samples. So what you see here is our first result, which uses a pre-estimated simulation of the domain. So this is the full domain, and you can see how the posterior solution moves across this domain. So this is the neural network representation of the posterior solution, and it moves from right to left through our domain. And here are some snapshots of the solution. So the black dotted line is the posterior estimated by the neural network. The yellow line is the prior neural network. So this is sort of the unnormalized neural network. And the blue line is a Monte Carlo reference solution of the Cauchy problem. And here you can also see how the solution moves. And in particular, you can see this on the upper left, you can see the sort of the curve in the blue line, which is the bimodality of the solution, which comes from the nonlinearity of the Banish filter. Here we are showing the error plots. So the first plot is the absolute error between the mean of the true solution and the mean of the posterior estimated by the neural network. And then on the top right, you can see the L2 error during training. So each line corresponds to one time step and represents the L2 error between the light blue line and the yellow line. So between the reference solution estimated by Monte Carlo of the PDE and the neural network solution of the PDE. And you can see in particular that during the training, this error consistently is going down. The lower left is the probability mass of our solution. And of course, it should be 1. But due to the inevitable numerical errors, it fluctuates around 1 somehow. And after the normalization, it's going to be exactly 1. And this is just to gauge how well things are working. And the lower right is the Monte Carlo acceptance rate. So since we have to estimate the mass of the neural network over the domain, we have to simulate the normal random variable. And if it lies outside of the domain of the neural network, we can't use it. And this is simply reflected in this Monte Carlo acceptance rate to see how well sort of the normalization is working. So the second example is now for our first iteration of the domain adapted method. So domain adapted here simply means that we have used, using the fixed random seed that I showed you for this realization, we have used the domain that was bounded by the 2 gray vertical lines, which are estimates of the support of the posterior computed a priori. So the challenge is to find a method which computes this online so that we can truly sort of online compute the result of the filtering. Here, this was pre-computed. This is just so to see that this works. So the domain moves with the solution, which is the desired behavior. And we can see in particular here, which is the point of this, we are using a nonlinear method. And as I said, one of the features of the nonlinearity is that we have this bimodality developing, especially in the initial part of the filtering. So you can see here that compared to the previous result, if we can leverage the increased resolution inside of the domain, which is still 1000 grid points, we can much better resolve the bimodality using the neural network than we can if we have the fixed domain. And here are the error plots. So the L2 error is still going down during the training, which is good. Monte Carlo acceptance rate remains high at around 95%. the probability mass looks fine. And sort of what is striking here is that there seems to be a linear trend in the error between the mean of the true solution and the mean of the neural network, which we don't completely understand yet, but we believe that it has to do with the fixed left boundary which the solution moves to. So if the solution gets closer to the left boundary, things start to get worse. But this remains to be investigated further. And with that, let me come to the conclusion of the talk. So what we have presented shows that online filtering for nonlinear models is possible using this deep learning approach. And one of the most important points is that the results are sensitive to the choice of the domain. So obviously the striking feature of this is that we are not dependent on the a priori domain, but still the choice is critical because we need to somehow accurately reflect on the solution, and the solution contains the support of the density, of course. So the domain adaptive method is more effective in resolving the nonlinearity and the nonlinear features due to the increased resolution. So computationally, it is desirable to have as accurate a domain as possible. I've talked about the linear trend in the error, which we're currently investigating. And as I said, it's critical to develop an effective method to do this domain adaptation online, which we expect to be to improve results even further. And then another point which we could do is, I showed you the algorithm which sort of includes an initialized neural network at each step. And since things are continuous, we would expect that sort of adapting the parameters that we already have using transfer learning would be more efficient in terms of computation resources. So we are also currently implementing the transfer learning strategy, and also the high dimensional applications, as Dan mentioned, are under investigation in relation to the Stewart project. And with that, I would like to close the talk, and thank you for your attention.
Thank you very much for these very nice presentations. So, are there any questions?
Hello, it was a very nice talk. It seemed very useful idea for filtering to use neural networks. My question is regarding the choice of using the regularization there for trying to get the output of the neural network to be positive. Did you try using your suggestion of using, say, the exponential of the output of the neural network?
We haven't done this computationally, but there are results in the literature that do this for other Fokker-Planck equations. And yeah, these two methods, they seem to be, I mean, both are working. For us, the regularization parameter approach did work. So we didn't use the other method, but there are results in the literature that also use this sort of exponentiation method, and it sort of works equally well, I would say.
Yeah, because you are also adding through the penalization another parameter to be tuned at the lambda. That's one thing that I thought that maybe could be avoided, or even allowing for a negative value, right?
Yeah, definitely. Yeah,
it could be totally problematic.
Right. I mean, yeah, it can be. On the other hand, since we haven't tested it computationally, I don't know about the behavior of the optimization method when you sort of use the exponential. So I don't know how it would behave in that.
Okay. A second question that I have is regarding the layout of your neural network. You used two hidden layers there. right? And I also observed that during your training for different cases, you reached some kind of threshold on the L2 error that you were achieving. I wonder if you tested increasing the number of hidden layers there to improve the generalization capabilities of your model and seeing if you can reach lower levels of your L2 error.
Yeah, we have. So we have tested especially with a larger layer width in order to sort of try and see if in terms of the approximation capability of the neural network, sort of things get better. But I mean, in the computational time that we were able to run these experiments, we haven't observed any better values with like a larger number of parameters. So we found this to be the sweet spot in our experiments.
Okay, thank you very much.
Mm-hmm.
Are there other questions? Just 1 second.
Thanks, Dan and Alex, for the nice presentation. So I have a question and a comment. The question is regarding the sensor function. You're assuming it's an affine map. Is this a necessary requirement for your neural network to work? And the comment is about estimating the normalizing constant using Monte Carlo. And I feel like this is a serious drawback of the method. If you move to not high dimensions, but even to moderate dimensions, how are you gonna estimate the normalizing constant? So
yeah.
the first question is again, is it necessary to assume the sensor function to be affine? And the other one is about computing the normalizing constant. Thank you.
Okay, yeah, these are very valid questions. So let me start with the second question. So I mean, it depends on what you see as a drawback, because sort of we are working on extending it for the high dimensional cases that we also have in our Stewart project, and there sort of computing the normalization constant in any other way that uses grids like quadrature and things, it simply becomes infeasible, because the runtime or the number of grid points that you would need in general would grow exponentially in the parameter d, which is the dimension. So you simply cannot do this in that case. So this is why we use Monte Carlo. So it's initially, of course, in one dimension, it's slow and you wouldn't do it. But as the dimension becomes higher, the Monte Carlo starts to help you. And in the second case, so the way that we presented the method here for the Benesch filter indeed uses the assumption that the sensor function is affine. But this does not mean that there can be sort of, you would need to see how to do the Monte Carlo estimation in the case where it's not affine. So you would need to derive the right law so that you can represent this integral as the expectation with respect to the right law in order to compute the normalization constant. So it is not completely restrictive, but you would need to sort of reformulate it if you have a different problem.
Can I just step in? The reason why the sensor function is chosen to be affine is because we wanted to use this benchmark, the Benesch filter. For the Benesch filter, the sensor function has to be affine, otherwise you don't get an explicit solution. You know, the nonlinearity for the Benesch filter occurs in the signal equation, but the sensor function has to be linear. That's why we use that. Now, the methodology, you know, is developed to be generic, regardless of the sensor function. But of course, we exploited the particular format of the sensor function here to do the integration and to do the steps, but the second step. But that doesn't mean that the methodology cannot be applied to a case where the sensor function is not affine. But that means in that case you won't have an explicit solution, so you will not know. I mean, of course, you could compare this with a particle filter. So I think that could be done rather than having the explicit solution.
Thank you very much. Are there any other questions? If not, then thank you very much, Alex. Thank you very much, Dan, for this very nice talk.
Thank
and
you.
as I said, Alex, you have introduced yourself very well. Thanks again.
Yeah, thank you very much.
Thank you. Bye.
And I think we have like a short break of 5 minutes and then we go on.